from the CVS, from the CVS repository logs that for 18 months, or yes, about 18 months, this PRNG had a huge bug where instead of reading n bytes, the PRNG was reading 4 times n bytes. You didn't get a blue screen because that's part of the kernel, and you don't have blue screens in Linux, of course. But actually, the mathematical functionality was wrong, very wrong. And it's critical. It is used by many, many security applications by default in Linux, including TCP, PGP, S-MIME, SSL. If you're running a web server on Linux, that's the PRNG you're most likely to use. Regarding functionality, there are 2 interfaces, one in the kernel and one for users. The one for the kernel is called getRandomBytes. That's a C function, which is used by any kernel function who needs random bytes. For example, the TCP sequence numbers are using this function. If you are implementing an application, whether you are a user or administrator, you probably are using one of 2 device drivers, dev random or dev urandom. That's your two options. And you can see here the definition of the writers, of the implementers of this entropy-based PRNG. The difference between them is they both use the same entropy, but dev random should be much more secure, whereas dev urandom is less secure, but is much faster. So kind of the instruction, if you read the manual, if you need extremely secure bits, use dev random. The penalty will be that you may be delayed till there is enough noise, enough entropy in the system. And if you're willing to give up some level of security, then use dev urandom, which works much faster. Actually, I'm going to show you in the next slide that it's not like that. There is no real difference between them. The entropy collection mechanism isn't correlated in the right way, unfortunately. So to implement this, there is a counter called entropy estimation, which measures how many different bits of entropy came from the operating system, entered the pool, the entropy pool, and whenever you extract, this counter is decreased. So whenever the system adds entropy, the counter gets increased. Whenever you consume, it decreased. Very simple. And for dev random, if this number gets to 0, you go to sleep. Your process goes to sleep till there is new entropy. For dev urandom, you get data forever. So that's the mechanism in very, very simple. I mentioned, and that's the last line of the slide, that actually there isn't a good relationship in the implementation. Actually, there isn't a good relationship between the entropy coming in and the entropy which you get. So actually, the pool can stand for a minute on 0. You can sleep, your process can sleep. You will be waiting for additional entropy to come. The entropy will come and will be entering some point of the pool, and then you will get entropy, but from another spot in the pool. So there is no real relation, just the counter, but the entropy comes from a different space. I mentioned, and when we first published it, I got lots of flames about our result. What kind of reverse engineering is it? That's not the reverse engineering at all. The code is there for you. That's so great about open source. I have nothing against open source. I think open source is great. But on the other hand, open source doesn't prove that things are secure. That's it. It doesn't prove. The fact that it was there for 12 years, okay. It isn't easy to read. It's about 2,500 lines of code, which is very, very complex to understand. It includes lots of mathematics, lots of complex changes, unfortunately some bugs, and reverse engineering, and as someone said in the early talk this morning, is not about reading the code. Some of us can read assembler very, very fast. It's about understanding what's the functionality of a model. So unfortunately, this wasn't an easy task. And someone asked me earlier, we were working on this one for more than a year. Also, because of the fact that it is part of the kernel, debugging and working with the kernel was a very complex task. And whenever you add changes, of course, to the kernel, you also influence some of your measurements, and that wasn't easy. So we did both static analysis from the code, some dynamic measurements through changing the code, and to make sure that our findings are correct, we also implemented a complete user mode simulator that you can download and you can run even without the kernel itself. And of course, that was the best way to verify that our findings are correct. So that's about reverse engineering. Here's the structure of the Linux random number generator in short. I'll go from left to right, and then we will get into more details about each of these elements. First, entropy is collected. Entropy is collected from 4 sources. These are keyboard typings, mouse events, hard disk movements, and interrupts. All these are collected asynchronously, and I'll get back to it, and enter to a large pool. Then there are 2 additional pools. One is called the secondary, and the other one is called the urandom. One of them is used for the secured interface, and another for the less secure one. And as you can see, I guess that some of you can feel it. It's a bad coupling right now. The entropy comes from a single source, from a single big pool, which used to feed the other 2. It's in a bad way. All of these, what marked in single letters, the C, the A, the collection, the addition, the extraction, each of them is a different procedure, and I'm going to get to it in details. And you can see also the dashed line, which says that whenever you extract entropy, you also add a feedback back into the pool. So it's quite a complex structure. Lots of assembler operations per each random byte that you read. Okay, first about the collection. The collection is quite simple. I mentioned that it is asynchronously, meaning whenever there is entropy in the system, it is collected. Collected, gathered, entered into the pool. So whenever you move the mouse, type something on your keyboard, it is entered to your entropy pool, which is good. That's what we want to do. Whenever there is entropy, let's use it. I mentioned Windows, and I can tell you that our early results from the Windows operating systems prove that, for example, in Windows, they do not use it in this way. They collect entropy only whenever you extract, when you need random bytes. So that's a better way. Collect entropy whenever there is. So for each event, we collect two words, two 32 bits of information. One of them is the event type, and the second is the timing in milliseconds of the event. So, for example, for keyboard, 32 bits for keyboard values, we don't need so many, right? How many do we need? 8. There are 256, that's it. No more than that. So some of it is redundant. Yeah, that's it. And for hard drive, if you have a single IDE drive in your machine, you get single value, fixed value, always the same. So there isn't much entropy coming from the event type. We actually do get a lot of entropy from the timing, from the millisecond of the event. That's where we get the entropy, the actual entropy. So the bad news is that the actual entropy in each event is very, very low because, as I mentioned, hard disk, almost none, keyboard, a little bit, mouse, there is some, and interrupts, by the way, are not implemented for all the devices. Interrupts are implemented just for certain device drivers in the operating system. So we get very few different values, but the good result is that we get a lot of them. Okay. Now to the math. I won't get into all the details, just to make sure that you get the picture. Each entropy addition, we take these values, the two 32-bit values, and add them to the pool. I'll go back. This is the addition is where you can see the letter A. So after we collect entropy, we do addition. That's on the entrance to the primary pool. When we add entropy to the secondary, again, we use the addition process. The addition process is a generalization of linear feedback shift register. It's a very simple mathematical operation. You can see it in the lower array. The G is actually the value coming from the operating system. That's the entropy, that's the noise, the 32-bit. And we XOR it with 5 different values from the pool and update another cell. So we take 5 values, the entropy, XOR it, multiply by some matrix, but that's not important, and enter it to one of the cells. That's entropy addition. Okay. How about extraction? Extraction is using SHA-1. And what we do, you can see here the pool that has 32 entries of pool. Each of them is a 32-bit entry. Okay, that's the smallest pool.